Right now, around Saturn, 2 moons are circling the planet on nearly the same path. Their orbits are separated by just 50 kilometers. That gap is smaller than either moon is wide. By every rule you know about gravity, they should have crashed into each other a long time ago. But they haven't. Instead, every 4 years, something stranger happens. The inner moon catches up to the outer moon, and just before they should collide, gravity rearranges them. One shifts outward, the other shifts inward, and they trade places. Then the cycle starts again. No collision, no catastrophe. Just a silent, repeating exchange that has been going on for longer than humans have existed. Tonight, you're going to understand exactly how 2 moons can share one orbit and never touch. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Let's begin. Saturn is surrounded by the most elaborate collection of moons and rings in the entire solar system. At current count, more than 140 confirmed natural satellites orbit this gas giant. They range in size from Titan, a moon so massive it holds a thick nitrogen atmosphere and supports liquid methane lakes on its surface, all the way down to unnamed irregular fragments, barely a few hundred meters across, tumbling silently through the darkness near the outer edges of the planet's rings. Some of Saturn's moons are famous. Enceladus shoots towering jets of water ice into space from fractures in its frozen southern crust, feeding an entire ring of Saturn with fresh particles. Titan hides a complete weather cycle beneath an opaque orange haze, with methane rain falling on methane rivers that drain into methane seas. Mimas carries a crater so disproportionately enormous that the moon looks like a single scarred, frozen eye staring out into the void. But tonight, we are not here for any of those moons. We are here for 2 that most people have never heard of. They are irregularly shaped, closer to battered potatoes than to spheres. They are made mostly of water ice, porous and ancient, and covered with craters. And they do something that, when you first learn about it, sounds like it should be physically impossible. Their names are Janus and Epimetheus, and they share an orbit around Saturn, not loosely, not approximately, not in the way that 2 cars on a wide highway might drift in and out of the same general lane. These 2 moons occupy nearly the same circular path around Saturn, at nearly the same distance from the planet's center. Janus orbits at approximately 151,460 kilometers from Saturn's center. Epimetheus orbits at approximately 151,410 kilometers. The difference between those 2 numbers is about 50 kilometers. That is the total radial gap between them. 50 kilometers of empty space between 2 paths that circle an enormous planet. To understand how absurdly small that number is, you need to compare it to the moons themselves. Janus, the larger of the pair, has a mean diameter of about 178 kilometers. If you measured it at its widest, it stretches roughly 203 kilometers across. Epimetheus, the smaller partner, has a mean diameter of about 117 kilometers, stretching to around 130 kilometers at its widest. Both moons are physically wider than the gap between their orbits. It would be as if 2 ocean liners were sailing on parallel courses, set closer together than the ships are long. You would look at that arrangement and immediately think it was a matter of time before they sideswiped each other. And the situation is even more precarious than that comparison suggests. Because both moons are not merely sharing the same general region of space, they are orbiting Saturn in the same direction, along nearly the same circle, in nearly the same orbital plane. They are not on crossing paths that briefly intersect, the way some asteroid orbits cross each other. They are on parallel tracks that run beside each other continuously, all the way around the planet, with a separation that never exceeds a few tens of kilometers. There is no point in their orbits where they diverge to a safe distance, and no point where their paths curve away from each other. They are always close. Now, you might wonder whether there is some geometric trick that keeps them safe. Maybe their orbits are tilted relative to each other, so that one moon passes above or below the other. That is how some asteroid orbits work in the solar system. Two orbits can cross in 2 dimensions, but be separated in 3 dimensions, because they are inclined at different angles. But Janus and Epimetheus do not have that luxury. Their orbital inclinations are tiny, less than half a degree from the same plane. They are, for all practical purposes, moving in the same flat disk around Saturn. There is no vertical separation saving them, and here is the part that makes the arrangement seem truly impossible. The inner orbit, the one that sits slightly closer to Saturn, is the faster orbit. That is not a detail specific to Saturn. It is a fundamental law of orbital mechanics, established by Johannes Kepler in the 17th century. A moon closer to a planet feels a stronger gravitational pull. That stronger pull means the moon must travel faster to maintain a stable orbit. A moon farther from a planet feels a weaker gravitational pull and moves more slowly. The relationship is precise. It is mathematical. It is inescapable. Closer means faster. Farther means slower. Always. The orbital periods of Janus and Epimetheus reflect this law with striking clarity. Each moon takes approximately 16 hours and 40 minutes to complete one full circuit of Saturn. But because the inner moon is slightly closer, it completes each orbit a little bit sooner, roughly 30 seconds faster per lap. That does not sound like much. 30 seconds out of nearly 17 hours is almost nothing. It is a difference so small that you would need extremely sensitive instruments to even measure it. But those 30 seconds accumulate. Every orbit, the moon on the inner track pulls slightly ahead of the moon on the outer track. One orbit, a fraction of a degree. 2 orbits, a fraction more. 100 orbits, a measurable angle. 1,000 orbits, a significant gap closing. Day after day, week after week, month after month, the inner moon creeps forward, gaining ground along the shared orbital circle, slowly closing the angular distance between itself and the outer moon. After about 4 Earth years, roughly 2,100 orbits, the inner moon has gained enough ground to come within roughly 10,000 to 15,000 kilometers of the outer moon. And at that point, every instinct tells you what should happen next. 2 solid objects, one overtaking the other on almost the same path, approaching within a few thousand kilometers with no atmosphere to create drag and no mechanism to steer them apart. In any ordinary situation, that ends in a collision. At orbital speeds, even a glancing impact would be catastrophic. The moons would shatter or deform. The debris would spread along the orbit and settle into a diffuse ring of rubble. That is the expected outcome. That is what the basic physics appears to demand. But that is not what happens. Not even close. Instead of colliding, Janus and Epimetheus do something far stranger. Every 4 Earth years, when the inner moon has closed the gap enough to bring them within gravitational range of each other. The two moons swap orbits. The moon that was on the inner track moves outward. The moon that was on the outer track moves inward. They trade positions cleanly and completely, without ever touching. The closest they come to each other during the entire exchange is roughly 10,000 to 15,000 kilometers. For reference, that is roughly comparable to the diameter of the Earth. There is never a moment of danger. There is never a near miss. The exchange happens gradually, over the course of about 100 days, and when it is finished, the moon that used to be closer to Saturn is now farther away, and the moon that used to be farther away is now closer. Then, the whole process resets. The new inner moon begins gaining on the new outer moon, and 4 years later, they swap again. This has been going on for an almost incomprehensible length of time. Conservative estimates suggest this orbital exchange has been repeating for millions of years. Some models place the origin of the system hundreds of millions of years in the past. Every 4 years, like a mechanism that never needs winding, the two moons approach, rearrange, and retreat. Approach, rearrange, retreat, over and over, in the silent vacuum around Saturn, with no observer and no purpose except the blind, reliable, patient workings of gravity. The story of how we discovered these two moons is by itself a remarkable illustration of just how strange their orbital arrangement is. Because for 12 years after astronomers first observed them, nobody realized there were two moons at all. Discovering small moons near Saturn has always been difficult. Saturn's rings are brilliant. They reflect enormous amounts of sunlight, creating a glare that washes out the faint light of any tiny moon orbiting nearby. It is like trying to spot a firefly hovering next to a searchlight. The firefly is there, but the searchlight blinds you to it. For most of Saturn's orbital period, the rings are tilted toward Earth at a significant angle, presenting a wide, bright surface that overwhelms everything close to the planet. But roughly every 15 years, as Saturn moves along its orbit around the Sun, the ring plane tilts until it aligns almost exactly with our line of sight. When that happens, the rings turn edge-on. They become a thin, faint line, almost invisible, and the glare drops dramatically. For a brief window of time, the region near the rings becomes observable. Small, faint moons that are otherwise lost in the brightness suddenly become detectable. 1966 was one of those windows. Saturn's rings were nearly edge-on as seen from Earth, and astronomers around the world took advantage of the opportunity to search for previously unknown moons. On December 15th of that year, a French astronomer named Audouin Dollfus was observing Saturn through the 1-meter telescope at the Pic du Midi Observatory, high in the French Pyrenees Mountains. Dollfus was a renowned visual observer, widely regarded as one of the finest of his generation. That night, he spotted a tiny point of light moving near Saturn's outer rings. It was clearly a satellite, a new moon, something no one had catalogued before. He noted its position, tracked its motion, and reported the discovery. The object was given the temporary designation S1966S2. Dollfus proposed naming it Janus, after the Roman god of doorways and transitions, the deity traditionally depicted with two faces looking simultaneously in opposite directions. 3 days later, on December 18th, an American astronomer named Richard Walker independently observed what appeared to be a moon in the same orbit around Saturn. He recorded its position carefully. But when Walker's positional measurements were compared with the data Dolphus had collected just 3 days earlier, something did not make sense. The positions could not be reconciled into a single consistent orbit for one object. The moon was apparently not where it should have been. It was as though the object had jumped from one part of its orbit to another, in a way that no single body on a smooth elliptical path could explain. At the time, nobody seriously considered the possibility that there might be two separate moons sharing the same orbit. That was not something anyone had observed before among planetary satellites. It was not something the standard models of moon formation predicted. The working assumption, reasonable and intuitive, was one orbit, one moon. Two objects on the same path should collide. Therefore, there could only be one object. And so astronomers tried to make the conflicting observations fit a single moon. They adjusted orbital parameters. They considered the possibility of measurement errors. They revisited the 1966 data again and again. The contradiction proved stubborn. It sat in the data like a splinter that could not be removed. In the years following the initial observations, other astronomers attempted their own measurements of the mysterious moon near Saturn's rings, and more data accumulated, but none of it resolved the problem cleanly. Each new observation seemed to add another inconsistency rather than settling the matter. There were even photographs taken earlier than Dolphus's observation. A French photographer named Jean Tex-Hérault had captured the moon on film as early as October of 1966 without recognizing what he had recorded. In 1979, the Pioneer 11 spacecraft flew past Saturn and detected what was likely one of the two moons in its imaging data. Though the limited number of frames made it impossible to calculate a reliable orbit from that encounter alone. For 12 years, the mystery lingered. Every attempt to model the orbit of this supposed single moon produced inconsistencies. One batch of observations implied a particular set of orbital elements. Another batch implied a slightly different set. The numbers kept refusing to agree, as though the moon were misbehaving, as though it did not want to be pinned down. Astronomers knew something was orbiting Saturn in that narrow gap near the outer rings, but they could not make the mathematics describe it as one thing. The breakthrough came in October of 1978. Two astronomers at the University of Arizona, Stephen Larson and John Fountain, proposed the explanation that had been hiding in plain sight. The 1966 observations, they argued, were not of one moon. They were of two moons, two separate, distinct objects sharing nearly the same orbital path around Saturn. Audouin Dolphus had observed one of them, Richard Walker had observed the other. The reason the orbital data would not reconcile was not that the measurements were flawed. It was that astronomers were attempting something mathematically impossible, fitting two separate trajectories into a single orbit. The moment you allowed for two bodies instead of one, every contradiction vanished, every discrepancy resolved. The positional data fell neatly into two distinct but nearly identical orbital tracks. Two moons, not one. It was a bold claim. Two moons on nearly the same orbit, close enough together that ground-based telescopes couldn't reliably tell them apart. Somehow coexisting without smashing into each other. It demanded a physical explanation. It required someone to demonstrate that two bodies could actually share the same orbital space around a planet and survive. But the observational evidence was strong and the mathematical fit was clean. 2 years later, in 1980, the Voyager 1 spacecraft flew through the Saturn system and turned its cameras toward the inner moon region. And there, In the images returned across hundreds of millions of kilometers of space, the question was settled for good. Voyager 1 photographed two clearly separate moons, both small, both irregularly shaped, both scarred with craters, and both orbiting in the narrow gap between Saturn's F-ring and G-ring, on orbital paths so similar that ground-based telescopes had spent over a decade confusing them for one object. In the Voyager 1 frames, you could see them plainly. Two lumpy, greyish bodies caught in reflected sunlight against the blackness of space, each one distinct. They were not colliding. They were not fragments of a recent breakup drifting apart. They were stable, coexisting, and following the same average orbit. The co-orbital configuration proposed by Larson and Fountain was not an artifact of poor measurements or a theoretical curiosity. It was a physical fact, confirmed by direct imaging from a spacecraft, and it was unlike anything else that had been documented anywhere in the solar system. In 1983, the International Astronomical Union officially named them. The larger moon kept the name Dollfuss had proposed 17 years earlier, Janus. Its formal designation became Saturn X. The smaller moon was named Epimetheus, with the formal designation Saturn XI. Both names carry a quiet resonance. Janus, the Roman god of transitions, of beginnings and endings, of doors and passages, was traditionally depicted with two faces, one looking forward and one looking back. It is a fitting name for a moon that periodically reverses its orbital position, alternating between inner and outer tracks, forever transitioning between two states. Epimetheus draws its name from Greek mythology. He was a Titan, the brother of Prometheus. While Prometheus represented foresight, the capacity to think ahead, Epimetheus represented afterthought, the understanding that arrives only after an event has passed. The name suits the smaller moon. It was the afterthought of the discovery, the second body whose existence was not recognized until years after the first observations had already been made. With the existence of two moons confirmed, astronomers could finally study them properly, and the more they learned, the more the strangeness of the system deepened. Janus is the larger and heavier partner. Its dimensions are roughly 203 kilometers by 186 kilometers by 149 kilometers. It is not a sphere. It is far too small for its own gravity to have pulled it into a round shape. Instead, it is a lumpy, battered, oblong chunk of ice, its form dictated more by the collisions it has absorbed over billions of years than by any tendency towards symmetry. Its mass is approximately 1.9 times 10 to the 18th kilograms. That is substantial by everyday standards, but by the standards of planetary satellites, it is tiny. Janus has roughly 1/40,000th in the mass of Earth's moon. Epimetheus is smaller in every dimension. It measures roughly 130 kilometers by 116 kilometers by 107 kilometers. Like Janus, it is irregular, cratered, and ancient, but it carries its own distinctive character. Close-up images returned by the Cassini spacecraft show a surface that is not merely pocked with craters, but scored with long ridges and grooves. Features that suggest internal stresses, perhaps fractures from past impacts that nearly shattered the moon but did not quite finish the job. Some of the larger craters on Epimetheus approach 30 kilometers across, occupying a significant fraction of the moon's entire visible face. At that scale, a single impact basin is roughly 1/4 the width of the moon itself. The surface tells a story of repeated violence absorbed and survived over billions of years. Its mass is approximately 5.3 times 10 to the 17th kilograms, making it roughly 3.6 times less massive than Janus. That mass ratio, Janus being about 3.6 times heavier, turns out to be one of the most important numbers in the entire system. It determines how the gravitational exchange between the two moons plays out, shaping the magnitude of the shift each moon experiences during every swap. This is something we will return to. Both moons share a remarkably low density, approximately 0.6 grams per cubic centimeter. To put that in perspective, the density of liquid water is 1 gram per cubic centimeter. These moons are less dense than water. If you could somehow transport either one to an ocean vast enough to hold it, the moon would float. This extraordinarily low density tells scientists something crucial about the internal structure of both objects. They are not solid, tightly packed bodies. They are porous. They almost certainly qualify as rubble piles, loose aggregations of icy fragments held together more by their own feeble gravity than by any material strength, riddled with internal voids and empty spaces. Imagine a mound of snow, built not by compressing it into a dense ball, but by carefully stacking chunks of ice against each other until they held under their own slight weight. That is roughly the structural character of Janus and Epimetheus. Both moons also have high albedos. They are bright, reflecting a large fraction of the sunlight that reaches them. Janus reflects approximately 71% of incoming light. Epimetheus reflects approximately 73%. This brightness, together with their low density, points strongly towards a composition dominated by water ice with only minor amounts of rocky impurities mixed in. And both moons are tidally locked to Saturn. Each one always keeps the same face pointed toward the planet, just as our moon always shows the same face to Earth. They rotate exactly once on their own axes for every orbit they complete, roughly once every 17 hours. This means that if you were standing on the Saturn-facing side of Janus, the planet would hang in your sky permanently, never rising and never setting, its rings stretching across the horizon in a display that would dwarf anything visible from any other vantage point in the solar system. Because of the moon's irregular shapes, this tidal locking has a visible geometric consequence. The longest axis of each moon points directly towards Saturn at all times, held in that orientation by the subtle but persistent gravitational difference between the near side and the far side of each body. Saturn's gravity grips them not just in their orbits, but in their orientations, controlling not only where they go, but which direction they face as they go there. Their surfaces are old. Both moons bear extensive cratering, with some impact basins exceeding 30 kilometers in diameter, enormous relative to the moon's overall size. The sheer density of craters tells us these surfaces have been exposed to the bombardment environment of the inner Saturn system for billions of years. Whatever process created these two moons, it happened very early in the history of Saturn's satellite system. That question, how Janus and Epimetheus ended up sharing the same orbit, remains an area of active scientific investigation. The leading hypotheses point in two directions. The first proposes that both moons were once a single, larger body that broke apart during a major collision. The fragments reassembled into two main pieces that settled into their current co-orbital arrangement. The nearly identical densities, compositions, and albedos of both moons support this idea. They look like they are made of the same material because they may once have been the same object. The second hypothesis ties the moons to Saturn's rings. Research published in the last 2 decades has demonstrated that Saturn's rings slowly spread outward over time, and when ring material drift past the Roche limit, the critical distance inside which Saturn's tidal forces tear apart any loosely bound objects, that material can begin to clump together and accrete into small moonlets. Some scientists have proposed that Janus and Epimetheus accreted independently from ring debris that drifted beyond this boundary at nearly the same orbital distance, forming 2 separate bodies on nearly the same path from the start. In this scenario, the moons were never one object. They were born as neighbors. Both ideas remain hypotheses. Neither has been conclusively confirmed, and the question of how 2 moons ended up in this configuration is still one of the open puzzles in planetary science. But what has been confirmed through decades of accumulating evidence from ground-based telescopes, the Hubble Space Telescope, Voyager 1, and most dramatically by the Cassini spacecraft during its 13 years orbiting Saturn from 2004 to 2017, is that the orbital exchange itself is real, stable, and repeating with extraordinary precision. Cassini tracked the positions of both moons through multiple swap cycles, measured the exact magnitude of each orbital shift, timed the exchanges down to specific dates, and recorded the gravitational ripples the swaps sent propagating through Saturn's rings. The data left no room for doubt. The exchange is not degrading. It is not slowly spiraling toward a collision. It is a self-sustaining cycle, maintained by the very gravitational forces that seem like they should destroy it. The most recent swap between Janus and Epimetheus took place in 2022. The next is expected around 2026. Right now, as you listen to this, these 2 small cratered icy moons are circling Saturn. One of them is on the inside track. One is on the outside track. The inner moon is gaining ground on the outer moon at a rate of roughly 1/4 degree per day, slowly, silently, inevitably. The gap between them is closing. And here is what remains unexplained so far. The fact that the inner moon catches up to the outer moon is straightforward. A closer orbit means faster motion. The gap closes over time. That part follows directly from Kepler's laws and requires no special explanation. But what happens when they get close? That is the part that defies your instincts. 2 objects converging on almost the same path around a planet should collide. Gravity should pull them together. The faster moon should overtake the slower moon, close the remaining distance, and strike it. That is what your intuition insists should happen, but it does not. The very force that seems like it should cause the collision, gravity, is the same force that prevents it. The gravitational interaction between Janus and Epimetheus does not pull them together. It rearranges them. It redirects their orbital energy. It shifts one moon outward and the other inward, swapping their positions with a precision that repeats every 4 years without variation and without contact. How that exchange actually works, the specific mechanics by which gravity turns an approaching collision into a clean orbital swap, is what we need to understand next. To understand how 2 moons can share an orbit without colliding, you first have to understand a rule about orbits that seems completely obvious until you realize it is hiding something deeply counterintuitive. The obvious part is this: a moon that orbits closer to Saturn moves faster than a moon that orbits farther away. This is one of the foundational principles of orbital mechanics. Johannes Kepler established it in the early 1600s, and it has been confirmed by every observation since. The closer you are to the object you are orbiting, the stronger the gravitational pull you feel, and the faster you must travel to maintain a stable circular path. Fall below that speed, and gravity drags you inward. Exceed it, and you climb outward. At any given orbital distance, there is exactly one speed that keeps you on a stable circle, and that speed is higher for closer orbits and lower for farther ones. You can see this principle at work throughout the solar system. Mercury, the closest planet to the Sun, screams along its orbit at about 47 kilometers per second. Earth, farther out, moves about 30 kilometers per second. Neptune, vastly more distant, drifts at just over 5 kilometers per second. The pattern is universal. Closer means faster. Farther means slower. It applies to planets around stars, moons around planets, and ring particles around Saturn. It is one of the most reliable rules in all of physics. It has never been observed to fail. Every object that has ever been tracked in orbit around another object obeys this relationship. And it has a direct, unavoidable consequence for anything that shares an orbital neighborhood with something else. Applied to Janus and Epimetheus, the rule is clear. Whichever moon is on the inner orbit at any given time is moving slightly faster than the moon on the outer orbit. Their orbits are separated by only about 50 kilometers. So the speed difference is tiny, just enough that the inner moon completes each circuit of Saturn roughly 30 seconds sooner. But those 30 seconds, compounding orbit after orbit, cause the inner moon to gain ground on the outer moon. Over the course of about 4 Earth years, the angular gap between them closes completely. The inner moon catches up. Now, here is where the counterintuitive part begins. And this part is essential. If you do not understand it, the orbital swap will never make sense. On a flat road, if you give a car more energy, it goes faster. Simple. Push harder on the accelerator, burn more fuel, and the car speeds up. Energy goes up, speed goes up. That is how things work in everyday life. But in orbit, the relationship between energy and speed is reversed. If you give an orbiting moon more energy, it does not speed up. It climbs to a higher orbit. And a higher orbit, as we just established, is a slower orbit. So adding energy to an orbiting object makes it go slower. Taking energy away makes it go faster. Energy up, speed down. Energy down, speed up. This feels wrong. It violates every instinct built by living on the surface of a planet where pushing something harder makes it move faster. But in orbital mechanics, most of the energy you add does not go into speed. It goes into height. It lifts the object farther away from the planet. And because a higher orbit requires less speed to maintain, the object ends up moving more slowly, even though it has more total energy. Think of a marble rolling inside a smooth, curved bowl. If you give the marble a push, it climbs higher up the wall of the bowl. At the top of that climb, it is moving slowly, almost pausing, before gravity pulls it back down. The energy you added went into lifting the marble, not into making it rush along the bottom of the bowl faster. Orbital mechanics works on a similar principle. Though the geometry is circular rather than back and forth, this paradox is not a quirk. It is the engine that drives the Janus Epimetheus swap. Everything that follows depends on this one fact. In orbit, gaining energy means climbing outward and slowing down, while losing energy means dropping inward and speeding up. The passing lane in orbit is always the lower lane. Spacecraft operators deal with this reversal every day. To catch a target ahead of it in orbit, a spacecraft fires its engines backward. It drops to a lower orbit, moves faster, and catches up. Then it fires forward to climb back up and rendezvous. Every docking maneuver at the International Space Station uses this principle. You go down to speed up, you go up to slow down. It is the fundamental trick of orbital navigation, and it is exactly the trick that gravity performs on Janus and Epimetheus every 4 years. Now, let us apply this to the two moons. Imagine the situation just before a swap. One moon is on the inner orbit, moving slightly faster, and it has been gaining on the outer moon for nearly 4 years. The angular gap has been shrinking, orbit by orbit, day by day, the difference accumulating with the mechanical inevitability of a clock hand advancing toward 12. Until the two moons are within roughly 10,000 to 15,000 kilometers of each other. They are not on a collision course. Their orbits are still separated radially by about 50 kilometers, inner versus outer. But they are now close enough, measured along the orbit, that their mutual gravitational attraction becomes significant. This is the critical moment. Up until now, the gravitational pull between Janus and Epimetheus has been negligible. They are small moons. Their masses are tiny compared to Saturn. At large separations, the gravitational force between them is overwhelmed by Saturn's gravity, which dominates everything in this region of space. But when the angular gap closes to the point where they are nearly side by side, separated along the orbit by only a few thousand kilometers, their mutual gravity can no longer be ignored. It is still small compared to Saturn's pull, but it is large enough to nudge their orbits. And in orbital mechanics, a small nudge at the right moment can change everything. Here is what happens. The inner moon is approaching the outer moon from behind. It is slightly closer to Saturn, slightly faster, and it has been creeping up on the outer moon for years. As it draws near, the gravitational pull between the two moons begins to act. The direction of that pull is not purely radial, not pointed straight toward or away from Saturn. It is pointed along the line connecting the two moons, which at this stage is nearly tangential to their shared orbit. The inner moon is behind and slightly below. The outer moon is ahead and slightly above. The gravitational force between them has a component along the direction of orbital motion. For the inner moon, the outer moon's gravity pulls it forward and slightly outward, forward along its orbit. This adds angular momentum to the inner moon. And what happens when an orbiting object gains angular momentum? It climbs to a higher orbit. Its orbital radius increases, and its orbital speed decreases. The inner moon begins to rise. For the outer moon, the inner moon's gravity pulls it backward and slightly inward. Backward against its direction of travel. This removes angular momentum from the outer moon. And what happens when an orbiting object loses angular momentum? It drops to a lower orbit. Its orbital radius decreases, and its orbital speed increases. The outer moon begins to fall. The two effects happen simultaneously. They are two sides of the same gravitational interaction, linked by Newton's third law. Every force has an equal and opposite reaction. The angular momentum that the inner moon gains is exactly the angular momentum that the outer moon loses. The total angular momentum of the system is conserved. Nothing is created, and nothing is destroyed. It is simply transferred from one moon to the other. And here is the key result. The moon that was on the inner orbit, the faster one, the one that had been catching up, gains energy and climbs outward. It moves to the higher orbit. It slows down. It stops gaining ground. In fact, it starts falling behind. Because it is now on the slower, outer track. Meanwhile, the moon that was on the outer orbit, the slower one, the one that had been getting caught, loses energy, and drops inward. It moves to the lower orbit. It speeds up. It begins to pull ahead. They have swapped. The inner moon is now the outer moon. The outer moon is now the inner moon. The one that was behind is now ahead, and the one that was ahead is now behind. And because the new inner moon is faster, it immediately begins gaining ground on the new outer moon. The cycle resets. 4 years later, they will approach again, exchange angular momentum again, and swap again. This is why they never collide. The very gravitational force that pulls them toward each other also rearranges their orbits in a way that pushes them apart. The approach triggers the exchange, and the exchange reverses the approach. It is a self-correcting mechanism built into the physics of the system. There is no external intervention. There is no fine-tuning. There is no lucky coincidence preventing disaster at the last moment. The geometry of orbital mechanics guarantees that two objects in this configuration will exchange positions rather than collide, as long as certain conditions about their masses and orbital separation are met, and those conditions are met by Janus and Epimetheus with remarkable, almost unsettling precision. But the swap is not symmetrical. This is where the mass difference between the two moons becomes important. Janus is roughly 3.6 times more massive than Epimetheus. Because angular momentum is conserved in the exchange, the lighter moon must absorb a larger change in orbit to balance the heavier moon's smaller change. It is the same principle as a seesaw. If a heavy adult sits on one end and a light child sits on the other, the child flies up much higher than the adult sinks down. The total torque balances, but the lighter object moves more. During each swap, Janus shifts its orbital radius by approximately 20 kilometers. Epimetheus shifts its orbital radius by approximately 80 kilometers. The ratio of those shifts, 80 to 20, is 4 to 1, which mirrors the inverse of their mass ratio. Janus barely moves. Epimetheus gets flung across a much wider band. If you plotted the orbital distance of each moon from Saturn over time on a graph spanning 25 years, you would see two dramatically different patterns. Janus traces a gentle, shallow zigzag, small steps up and small steps down, barely deviating from its average position. It looks almost like a straight line with minor wobbles. Epimetheus, on the same graph, traces dramatic jumps, leaping 80 kilometers outward and then 80 kilometers inward every 4 years, with sharp transitions that look like a square wave. The two moons share the same dance, but their experiences of that dance are profoundly different. Janus is the heavy partner barely shifting its weight. Epimetheus is the light partner being swung wide on every turn. And yet, the exchange is perfectly balanced. The angular momentum Janus gives up during each inward shift is exactly equal to the angular momentum Epimetheus gains during its corresponding outward shift, and vice versa. The accounting is exact, enforced not by any external bookkeeper, but by the conservation laws that govern all gravitational interactions. The entire exchange, from the first detectable gravitational interaction to the completion of the orbital swap, takes approximately 100 days. That is a little over 3 months. For most of the 4-year cycle, the two moons are far apart along the orbit, and their mutual gravity is irrelevant. They circle Saturn independently, each following its own path as though the other did not exist. Janus orbits, Epimetheus orbits. Each one rises and sets over Saturn's cloud tops every 17 hours, locked in synchronous rotation, presenting the same cratered face to the planet throughout. The only clue that anything unusual is happening is the slow, steady closure of the angular gap between them, a fraction of a degree per day, invisible to any observer without precise instruments. And then, over the span of roughly 100 days, the approach reaches its threshold, the gravitational hands reach across the gap, angular momentum transfers, orbits shift, and the two moons separate onto their new tracks. The 100 days of interaction are followed by roughly 1,300 days of quiet coasting. The drama occupies less than 7% of each cycle. The rest is patience. The pattern repeats every 4 years, but the full cycle, the time it takes for both moons to return to their original configuration, takes 8 years. This is because each swap reverses the roles. After one swap, the moon that was inner is now outer. After the next swap, 4 years later, they return to their original arrangement. So the system has an 8-year periodicity. 4 years on the inner track, then a swap. 4 years on the outer track, then another swap. And back to the beginning. There is a way to visualize this that makes the entire pattern snap into focus. But it requires a shift in perspective. Instead of watching the moons from a fixed point in space, imagine riding along with them. Imagine you are sitting in a reference frame that rotates around Saturn at the average angular velocity of Janus and Epimetheus. In this rotating frame, Saturn is stationary. The average orbital position of the two moons is stationary, and the individual motions of the moons appear as slow drifts back and forth relative to that average position. In this rotating reference frame, each moon traces a path that looks like a horseshoe. Not a literal horseshoe, but the mathematical curve that bears the name. The moon drifts forward along the orbit in one direction, reaches a turning point, reverses, drifts back the other way, reaches another turning point, reverses again, and repeats. The turning points are the orbital swaps. The forward drift is the period when the moon is on the inner orbit, moving faster than the rotating frame, creeping ahead. The backward drift is the period when the moon is on the outer orbit, moving slower than the frame, falling behind. The reversal at each end of the horseshoe is the gravitational exchange that swaps the orbits. If you trace this motion on paper, you would see the path curl in from one side, swing close to a turning point, sweep outward in a wide arc, and sweep back. The open end of the horseshoe always points toward the location of the other moon. The two moons take turns occupying opposite legs, one drifting forward while the other drifts back, then reversing. They are like two performers in a circular hallway, each walking toward the other, then turning around just before they meet and walking the other way. They share the hallway, but never actually pass each other. Janus traces a narrow horseshoe because its mass makes it resistant to large orbital shifts. Epimetheus traces a wider horseshoe because its lower mass makes it more responsive. But both horseshoes are open at the same point, the point where the other moon sits. The two horseshoes interlock, but never overlap. Neither moon ever passes through the gap where the other moon's horseshoe opens. They approach that gap, feel the gravitational interaction, and reverse direction before reaching it. This is why they never complete a full lap relative to each other. They never pass. They approach, swap, and retreat. Approach, swap, retreat. The horseshoe shape is the geometric signature of a co-orbital system, locked in a one-to-one resonance with mutual gravitational exchange. This type of orbit, a horseshoe orbit in a one-to-one resonance, was first described mathematically in the early 20th century. But Janus and Epimetheus were the first real-world example ever confirmed, and they remain, to this day, the only known case in the solar system where two objects of comparable mass execute mutual horseshoe orbits around a common parent body. There are other co-orbital objects elsewhere. Earth has a few small asteroids that trace horseshoe paths relative to our planet, but those objects are so vanishingly tiny compared to Earth that the resemblance ends at the mere shape of the path. Why that difference matters will soon become clear. Janus and Epimetheus are fundamentally different. Their mass ratio is about 3.6 to 1. That is close enough that both objects are significantly affected by the exchange. Both moons shift, both moons change orbits, both moons trace horseshoes. The interaction is genuinely mutual in a way that no other known co-orbital system in the solar system replicates. When Janus pulls on Epimetheus, Epimetheus pulls back with equal force, and both of them move. It is a two-way conversation, not a monologue, and that mutuality is what makes the system so dynamically rich and so scientifically important. And the system is stable. That is perhaps the most surprising part of all. You might expect that a configuration this delicate, two moons balanced on nearly the same orbit, exchanging positions every 4 years through a precise gravitational interaction, would be fragile. You might expect that any small perturbation, a stray gravitational tug from another moon, a slight asymmetry in Saturn's gravitational field, an ancient impact that changed one moon's velocity by a tiny amount, would destabilize the system and send the moons spiraling into each other or drifting apart. But that is not what happens. The system is robustly stable. The orbital swap acts as a restoring mechanism. If one moon drifts slightly from its expected position due to a perturbation, the next gravitational encounter corrects the drift. If a perturbation pushes Epimetheus to a slightly higher orbit than expected, the next exchange compensates, shifting it back toward the average. If a micrometeorite impact alters the velocity of Janus, the system absorbs that change across subsequent swaps until the deviation has been smoothed away. The system does not require perfection to function. It tolerates small deviations and self-corrects. This is not a system balanced on a knife's edge. It is a system sitting in a gravitational valley, and any push away from equilibrium is met by a force that pushes it back. Physicists call this kind of stability a stable libration. The system oscillates gently around its equilibrium state, always returning toward the center rather than running away from it. Theoretical analyses, beginning with landmark work by Stanley Dermott and Carl Murray in 1981, and extended by Charles Yoder and colleagues shortly after, demonstrated that the co-orbital configuration of Janus and Epimetheus is dynamically stable over extremely long timescales. The system can persist for millions of years, possibly much longer, as long as no catastrophic external event disrupts it. The gravitational perturbations from Saturn's other moons, the oblateness of Saturn itself, the subtle and continuous tidal interactions between the moons and Saturn's rings, none of these forces are strong enough to break the lock. The horseshoe configuration endures. This stability is encoded in conservation laws. Angular momentum is conserved during each exchange. The total energy of the two-moon system is conserved. The exchange does not dissipate energy or bleed momentum into the surrounding environment in any significant way. It is, in the language of physics, a conservative interaction. What one moon gives, the other receives. What one moon loses, the other gains. The books balance every time, and as long as the books balance, the cycle continues. There is no friction wearing the mechanism down. There is no energy leak, slowly draining the system of its ability to function. Unlike a mechanical clock, which eventually winds down and stops, this gravitational clock runs on the infinite patience of gravity itself. It needs no winding. It needs no maintenance. It simply operates, swap after swap, as long as the moons exist and the laws of physics hold. There is one additional subtlety worth understanding, because it reveals how tightly the mechanism is constrained. The distance at which the gravitational exchange occurs, about 10,000 to 15,000 kilometers, is not a coincidence. It is set by the masses of the moons and their orbital separation. If the moons were more massive, they would begin to interact at a greater distance, and the swap would happen over a longer arc of the orbit. If they were less massive, they would need to approach more closely before their mutual gravity mattered, and the swap would happen over a shorter arc. If the orbital separation were larger, the speed difference between inner and outer orbits would be greater. The closing rate would be faster, and the interaction would be briefer and more violent. If the separation was smaller, the closing rate would be slower, and the interaction would be more gradual. The specific configuration of Janus and Epimetheus, with their particular masses, their particular 50-kilometer orbital separation, and their particular position in Saturn's gravitational field, produces swaps that are gentle enough to be stable, but strong enough to be effective. The exchange shifts their orbits by just the right amount to reverse the convergence and reset the cycle, not too much, which would send them oscillating wildly, not too little, which would allow the inner moon to overtake the outer moon entirely, just enough. And this precision is not designed. Nobody tuned these parameters. The system arrived at this configuration through whatever process created it, whether that was the breakup of a single parent body or the accretion of two separate objects from Saturn's ring material, and the physics did the rest. The stability of the horseshoe orbit is a mathematical consequence of the gravitational interaction. It does not require intent. It requires only mass, distance, and the laws that govern how objects move under gravity. The swap itself, when it happens, is invisible to the casual observer. There is no flash, no sound, of course, in the vacuum of space, no visible change in the moon's appearances. They do not glow. They do not crack. They do not shudder or spin or deform. If you were watching from a telescope on Earth, you would not see two moons dramatically changing places. You would see two tiny points of light, barely distinguishable from each other against the glare of Saturn's rings, slowly shifting their angular positions relative to the planet over the course of weeks and months. The drama is entirely in the numbers, in the orbital radii, in the velocities, in the mathematical description of two paths that quietly trade places while the moons themselves continue their silent, cratered, icy tumble through the dark. Nothing about their surfaces records the moment. Nothing about their rotations marks the transition. Only their distances from Saturn change, and those distances change by amounts so small, 20 kilometers for Janus, 80 for Epimetheus, that you need a spacecraft with finely calibrated instruments to measure the difference at all. But the consequences of the swap are not invisible. Every time Janus and Epimetheus exchange orbits, the shift in their positions sends a gravitational signal outward through Saturn's system. Their orbital resonances with ring particles change. The locations where their gravity reinforces the natural oscillations of ring material shift by a few tens of kilometers, enough to alter the structure of nearby ring edges. The density waves they excite in the rings carry a record of the swap, written in the spacing and amplitude of tiny corrugations in the ring material. When Cassini arrived at Saturn in 2004, it carried instruments precise enough to read those records. And what it found confirmed that the orbital dance of Janus and Epimetheus is not just a curiosity of two small moons. It is an active force shaping the structure of Saturn's rings. The swap reaches beyond the moons themselves. It propagates outward through the ring system, sculpting edges, driving waves, and leaving signatures that a spacecraft 4 billion kilometers from Earth could detect and decode. That connection between two small moons swapping orbits in a quiet corner of the Saturn system and the vast, intricate, shimmering structure of Saturn's rings is where the story goes next. We know the swap rearranges the moons, but it also rearranges the rings. Every time Janus and Epimetheus exchange orbits, the shift in their position sends a gravitational signal outward through Saturn's ring system. That signal disturbs the orbits of nearby particles. It leaves physical marks in the structure of Saturn's most visible feature. Two small moons reshaping a structure billions of times their combined mass. To understand how, you need to see the environment these moons live in. And that environment is, by any measure, one of the most intricate gravitational landscapes in the known solar system. Saturn's ring system stretches roughly 282,000 kilometers across the full diameter of its main disk, measured from one side to the other. If you could peel the rings off Saturn and lay them flat, they would span nearly 3/4 of the distance from the Earth to the Moon. But their thickness, in most places, is astonishingly small. The main rings are typically only about 10 meters thick. Some regions may be thinner. The rings are vast in width and almost non-existent in depth. They are like a sheet of paper scaled to the size of a football field, except that the sheet is composed not of continuous material, but of trillions upon trillions of individual particles. Ice fragments mostly, ranging in size from grains smaller than a millimeter to boulders the size of houses. All orbiting Saturn independently, each one a tiny moon in its own right, each one following the same Keplerian rules we discussed earlier. Closer to Saturn means faster, farther means slower, and each one subject to the gravitational influence of every significant moon orbiting nearby. The particles jostle, collide gently, drift inward and outward under the competing influences of Saturn's gravity, mutual collisions, and the periodic tugs of distant moons. From a distance, the rings look serene, smooth, and luminous. Up close, they are a restless sea of ice, churning with structure at every scale. The rings are divided into distinct bands, labeled with letters that reflect the order in which they were discovered, rather than their position. The D-ring is the innermost, faint and tenuous. Then comes the C-ring, the B-ring, the A-ring, the narrow F-ring, the diffuse G-ring, and finally, the enormous but sparse E-ring that extends far beyond the main system. Between the B-ring and the A-ring lies the Cassini division, a prominent gap roughly 4,800 kilometers wide, maintained by orbital resonances with the moon Mimas. Narrower gaps exist elsewhere, each one carved by the gravitational influence of one moon or another. Janus and Epimetheus orbit in the space between the F-ring and the G-ring, just outside the dense, bright main ring system. They are not embedded in the rings themselves, but they are close enough that their gravitational influence reaches inward, and interacts with ring particles at specific distances. That interaction happens through a phenomenon called orbital resonance. And orbital resonance is the key to understanding how two small moons can sculpt the structure of a ring system billions of times more massive than they are. Here is how it works. Every ring particle orbits Saturn at its own speed, determined by its distance from the planet. At certain specific distances, a ring particle's orbital period happens to form a simple ratio with the orbital period of a nearby moon. For example, a particle might orbit Saturn exactly 7 times for every 6 orbits of Janus. That is a 7-to-6 resonance. Or a particle might orbit exactly 2 times for every 1 orbit of a different moon. That is a 2-to-1 resonance. These ratios matter because they mean the particle and the moon keep meeting at the same relative positions, over and over, orbit after orbit. Imagine pushing a child on a swing. If you push randomly, sometimes your pushes help the swing, and sometimes they fight it. The effect averages out to almost nothing. But if you push at exactly the right moment every time, at the same point in the swing's arc, the pushes accumulate. Each one adds a little energy. The amplitude builds. A tiny push, repeated at the right rhythm, produces a large effect over time. That is resonance. It is the amplification of a small force through precise timing. Orbital resonance works the same way. A ring particle at a resonant distance from a moon encounters that moon's gravitational pull at the same point in its orbit, over and over. Each encounter gives the particle a small tug. And because the tugs always come at the same orbital position, they do not cancel out. They accumulate. Over hundreds and thousands of orbits, these tiny rhythmic gravitational nudges compress and stretch the ring material at that distance, creating organized patterns that would not exist without the moon's influence. Density waves are the most common result. These are essentially spiral compressions propagating through the ring like sound waves through air, tightly wound spirals of alternating high density and low density bands that trail outward from the resonance location. If you could view a density wave from above, it would look like the grooves of a vinyl record, a series of tightly packed concentric ridges spiraling outward, each ridge representing a zone where ring particles have been compressed together by the accumulated gravitational tugs. Bending waves are the vertical counterpart. They warp the ring plane itself, lifting particles above and below the ring's average position in a rippling pattern, like a flag waving slowly in a gentle breeze. And at certain critical resonance locations, the accumulated tugs are strong enough to clear material out entirely, carving gaps and shaping edges with surgical precision. Saturn's rings are written through with these resonant signatures. Hundreds of density waves and bending waves have been identified, each one traceable to a specific moon and a specific orbital resonance. The Cassini spacecraft catalogued them in extraordinary detail over its 13-year mission. Cassini used stellar occultations, where the light of a distant star passes through the rings and the resulting brightness variations reveal structure invisible to direct imaging, to probe the rings at resolutions finer than anything previously possible. And it used direct imaging at resolutions that could distinguish features only a few hundred meters across, revealing fine structure that had never been seen before and in many cases had not even been predicted. What Cassini revealed was that the rings are not smooth. They are corrugated, layered, textured by the gravitational fingerprints of every significant moon in Saturn's inner system. Each wave, each gap, each edge is a message written in the language of orbital resonance. And Janus and Epimetheus leave some of the most remarkable fingerprints of all, because their fingerprints change. The most important resonance between Janus and the rings is the 7-6 resonance with the outer edge of the A-ring. At this distance, ring particles orbit Saturn exactly 7 times for every 6 orbits of Janus. This resonance falls almost exactly at the location where the A-ring ends, roughly 136,770 kilometers from Saturn's center. It is not a coincidence that the ring edge is there. The resonance helps to define it. The repeated gravitational tugs from Janus at this precise ratio reinforce a pattern in the ring particles' orbits, and that pattern maintains a sharp boundary. Without the resonance, the ring edge would likely be more diffuse, more gradual. The resonance acts like a wall of gravitational pressure, holding the ring material in place. But here is what makes this particular resonance unique. When Janus is on the inner orbit, its 7-6 resonance falls almost exactly at the ring edge, only about 4 kilometers inside it. At that position, the resonance is close enough to dominate the ring edge's behavior. It creates a distinctive pattern. 7 evenly spaced lobes in the ring edge, bumps and dips that make the outer boundary of the A-ring look like a gently scalloped circle rather than a smooth one. These lobes have a radial amplitude of roughly 12 to 14 kilometers, and one of the 7 dips aligns with Janus's orbital position. The pattern rotates around Saturn with Janus, as if the moon were a hand pressing 7 equally spaced dimples into the edge of a spinning disk of clay. Cassini observed this 7-lobed pattern in detail between 2006 and 2010, when Janus was on the inner leg of its orbital swap. Over 5,000 images and more than 170 stellar occultations of the A-ring edge were analysed. The pattern was clear, consistent, and exactly as the resonance theory predicted. Then, in January of 2010, Janus and Epimetheus swapped orbits. Janus moved outward. Its orbital radius increased by about 20 kilometers. And that 20-kilometer shift was enough to move the 7-6 resonance away from the ring edge. The resonance location shifted to roughly 136,785 kilometers, now about 15 kilometers outside the mean radius of the ring edge. The resonance was still there. Janus was still orbiting, but the resonance was no longer at the right distance to shape the ring edge directly, and the 7-lobed pattern vanished, not gradually, not over many months of slow fading. Within a relatively short period after the swap, the 7-lobed pattern, which had been the dominant structure on the A-ring's outer boundary for the previous 4 years, simply ceased to exist once the resonance moved away from the edge. The ring edge did not become featureless. Other, smaller resonant interactions from Mimas, Prometheus, Pandora, and Epimetheus itself continued to operate, creating their own complex but lower amplitude patterns. But the clean, dominant, 7-lobed shape imposed by Janus was gone. The ring edge took on a more complex, less organized appearance, no longer governed by a single overwhelming resonant force. Scientists analyzing the Cassini data described it as the difference between a clearly tuned instrument playing a single note and a room full of instruments, each playing quietly at once. The dominant note had been switched off. 4 years later, when Janus swapped back to the inner orbit, the 7-6 resonance returned to the ring edge, and the 7-lobed pattern reappeared. On schedule, predictably. The same 7 lobes, the same amplitude, the same alignment with Janus's orbital longitude. Like a signal being switched on and off every 4 years by the orbital dance of two small moons thousands of kilometers away from the ring they were sculpting. The ring had no memory of the pattern during the years it was absent. It simply reformed, imposed fresh by the returning resonance, as if the intervening 4 years had never happened. This is an extraordinary demonstration of gravitational cause and effect. Two moons exchange orbits. One of them shifts by 20 kilometers. That shift moves a resonance by 19 kilometers. And that 19-kilometer shift turns off a pattern 12 kilometers tall on the edge of a ring that is 136,000 kilometers from Saturn's center. The entire sequence is connected, each piece linked to the next by gravity alone, across distances and scales that span several orders of magnitude. Cassini's instruments recorded this cycle from inside the Saturn system, watching the ring edge reshape itself in real time as the moons swapped. The data confirmed that the A-ring's outer edge is not a static boundary. It is a living structure, dynamically maintained by a resonance whose location depends on which orbital track Janus happens to occupy at that moment. The ring is responsive to the moons. The moons are responsive to each other. And the entire system is locked into a cycle that repeats with the precision of a mechanism. But the 7 to 6 resonance with the A-ring edge is not the only mark Janus and Epimetheus leave on the ring system. Both moons also drive density waves deeper within the rings. The Janus 2-to-1 resonance generates a prominent density wave in the B ring. This wave has its own complication. Because Janus swaps between inner and outer orbital tracks every 4 years, the pattern speed of the resonance shifts slightly with each swap. Density waves propagate outward from the resonance location at a finite speed. So sections of the wave generated during different orbital configurations carry different pattern speeds. When these sections meet, they interfere with each other, producing distinctive disruptions in the wave profile. Glitches that scientists have used to reconstruct the history of Janus's orbital swaps by reading them backward out of the ring structure. The rings carry a record. Every swap leaves a mark, and a careful enough observer can read those marks like tree rings, each one corresponding to a specific 4-year interval. Cassini also discovered something entirely unexpected in 2006. While imaging Saturn at an extremely high phase angle, with the sun almost directly behind the planet so that forward scattered light from fine dust particles became visible, Cassini's wide-angle camera detected a faint, diffuse ring coincident with the orbits of Janus and Epimetheus. This ring, now called the Janus Epimetheus ring, is not a dense structure like the main rings. It is a tenuous band of microscopic dust particles, so faint that it was invisible in all previous observations. The particles are tiny, mostly between 1 and 4 micrometers in radius, specks of ice and dust far too small to see individually, and they are produced by micrometeorite impacts on the surfaces of both moons. When a high-speed dust grain strikes Janus or Epimetheus at several kilometers per second, it kicks debris off the surface in a spray of ejecta. Some of that debris achieves enough velocity to escape the moon's feeble gravity and enter orbit around Saturn. The ejected particles settle into orbits similar to those of the source moons, forming a faint dusty halo that traces the same orbital path. The Janus Epimetheus ring has a short lifespan. Individual particles survive in orbit for only about 15 years on average before they're destroyed by collisions with other dust or dragged inward by subtle forces like light pressure and plasma drag. But the ring persists because it is constantly replenished. As long as micrometeorite impacts continue to erode the surfaces of Janus and Epimetheus, and they will continue as long as the moons exist, fresh dust is injected into the ring to replace what is lost. It is a steady state structure, continuously dying and continuously being reborn, maintained in equilibrium by the balance between destruction and production. Now, Janus and Epimetheus are not the only moons in Saturn's system that share an orbit with something else. In fact, Saturn hosts the only known examples of Trojan moons, moons that share an orbit with a larger moon by occupying one of the stable gravitational niches, known as Lagrange points. Lagrange points are positions in the orbital plane of two massive bodies, in this case Saturn and a large moon, where the combined gravitational pull of both bodies and the centrifugal force of the orbits create pockets of relative stability. There are 5 such points for any two-body system, labelled L1 through L5. 2 of them, L4 and L5, are particularly important. They sit 60 degrees ahead of and 60 degrees behind the smaller body along its orbit. Objects placed near L4 or L5 tend to stay there, librating gently around the point rather than drifting away. They are gravitational parking spots. Saturn's moon Tethys, which is roughly 1,066 kilometers across, has 2 Trojan companions. Telesto, about 24 kilometers in diameter, leads Tethys by 60 degrees at the L4 point. Calypso, about 22 kilometers across, trails Tethys by 60 degrees at L5. These tiny moons have been orbiting in Tethys's gravitational shadow for eons, locked in place by the balance of forces at the Lagrange points. They do not swap orbits with Tethys. They do not exchange angular momentum with it in any significant way. They do not periodically change their distance from Saturn. They simply follow along, faithful companions occupying fixed seats on a larger moon's orbital circuit. If Tethys is a locomotive, Telesto and Calypso are the cabooses, always the same distance behind and ahead, never gaining or losing ground, never switching tracks. Similarly, Saturn's moon Dione, about 1,118 kilometers across, has its own pair of Trojans. Helene, roughly 36 kilometers wide, leads at L4. Polydeuces, only about 3 kilometers across and discovered by Cassini in 2004, trails at L5. Same arrangement, same stability. Small moons riding in the gravitational wake of a much larger one. These Trojan configurations are fundamentally different from what Janus and Epimetheus do. In a Trojan system, the relationship is lopsided. One body is vastly more massive than the other. Tethys outweighs Telesto by a factor of many thousands. Dione outweighs Polydeuces by an even greater margin. The larger moon dominates the gravitational landscape completely. The Trojan moon is a passenger, not a partner. It responds to the larger moon's gravity, but exerts no measurable influence in return. The orbit of the smaller moon is called a tadpole orbit, because in a rotating reference frame, the small moon traces a path shaped like a tadpole, looping around its Lagrange point without ever straying far from it. Janus and Epimetheus do something entirely different. Their mass ratio is only about 3.6 to 1. Both moons matter. Both moons move. Both moons feel the consequences of every exchange. The gravitational interaction is mutual and measurable on both sides. And the orbital pattern they trace is not a tadpole, but a horseshoe, sweeping back and forth across the full span of the orbit, rather than hovering near a single stable point. In the taxonomy of co-orbital motion, tadpole orbits and horseshoe orbits are distinct dynamical families. Tadpole orbits cluster near L4 and L5, small librations around a fixed point. Horseshoe orbits encompass L3, L4, and L5, sweeping the full arc between them. And while tadpole configurations are relatively common in the solar system, found among Jupiter's thousands of Trojan asteroids, among Saturn's Trojan moons, and even among some small bodies near Earth, horseshoe configurations between two objects of comparable mass are vanishingly rare. Janus and Epimetheus are the only confirmed example anywhere in the solar system. This makes their system not just unusual, but scientifically unique. A singular natural laboratory. It is the only place we have for studying how two bodies of similar mass behave in a mutual horseshoe resonance over long timescales. Everything we know about the dynamics of this kind of interaction, the stability conditions, the energy exchange rates, the sensitivity to perturbations, comes from observing and modeling these two moons. If they did not exist, the horseshoe resonance between comparable massive objects would be a purely theoretical construct. Something predicted by equations but never confirmed by observation. Janus and Epimetheus are the confirmation, and they exist inside a system that is itself an interconnected gravitational machine of breathtaking complexity. Saturn, its rings, and its moons do not operate independently. They are coupled. The moons sculpt the rings through resonances. The rings push back on the moons through the angular momentum those resonances transfer, slowly altering the moon's orbits over millions of years. The shepherd moons Prometheus and Pandora confine the narrow F ring from either side, their gravity pinching the ring material into a thin, braided strand that twists and kinks in ways that kept Cassini scientists occupied for years. The tiny moon Pan, only about 28 kilometers across, clears the Encke gap within the A ring, sweeping a clean lane through the ring particles and accumulating a thin ridge of material around its equator in the process. Daphnis, even smaller than Pan at roughly 8 kilometers, maintains the narrower Keeler gap, its gravity creating visible ripples in the gap edges that trail behind it like the wake of a boat. The gravity of Mimas holds open the Cassini division, the most prominent gap in the entire ring system. Every gap, every edge, every wave in the ring system is maintained by the gravitational influence of specific moons, each one exerting its pull at specific resonance locations, each one contributing its piece to the structure of the whole. Janus and Epimetheus fit into this interconnected machine in their own peculiar way. They are not shepherd moons confining a ring. They are not gap-clearing moons carving lanes. They are co-orbital moons whose periodic position swap toggles the gravitational influence they exert on the rings, turning resonant patterns on and off in a 4-year cycle. They are unique in this role. No other moons in Saturn's system do what they do. No other moons anywhere in the solar system do what they do. And the fact that their influence on the rings can be tracked so precisely, that the seven-lobed pattern appears and disappears on a schedule dictated by the orbital swap, demonstrates something important about the nature of Saturn's ring-moon system. It is not chaotic. It is not random. It is governed. The structure of the rings at any given moment is the result of specific gravitational forces acting at specific locations, produced by specific moons orbiting at specific distances. Change one moon's position by 20 kilometers, and the rings respond, predictably, measurably, within the time frame of a single Cassini orbit. The system is a gravitational clockwork, not in the sense of a design machine, but in the sense of a system where every moving part is connected to every other moving part through the invisible threads of gravitational influence. Pull one thread and the whole web shifts. Push one moon to a different orbit and the rings rearrange. The moons shape the rings. The rings slow the moons. The resonances maintain the edges. The edges define the gaps. The gaps host more moons. And those moons generate more resonances. Everything is linked. Janus and Epimetheus are a single component of this larger mechanism. A small one measured by mass, but a distinctive one measured by behavior. Because their periodic orbital swap introduces something no other component provides. A repeating, predictable, 4-year oscillation that propagates through the ring system and leaves a record in the structure of the rings themselves. They are the only part of Saturn's gravitational clockwork that ticks on a human observable timescale, short enough for a spacecraft mission to witness the full cycle, long enough for each phase to leave a measurable imprint. The Cassini mission ended on September 15th, 2017, when the spacecraft was deliberately plunged into Saturn's atmosphere to prevent any possibility of contaminating the potentially habitable moons Enceladus or Titan. After 20 years in space, 13 of them orbiting Saturn, Cassini burned up and was destroyed in the upper atmosphere of the very planet it had studied for so long. But the data it returned, nearly 635 gigabytes of scientific measurements, continues to be analysed years later. Within that archive are the precise records of Janus and Epimetheus swapping orbits, the records of ring edges reshaping themselves in response, the records of density wave glitches encoding the orbital history of the co-orbital moons like layers in a geological formation, and the faint glow of the Janus Epimetheus ring catching forward scattered sunlight in images no one had expected to find before Cassini arrived. No spacecraft currently orbits Saturn. No camera watches the rings reshape themselves. The next dedicated mission to the Saturn system remains in the planning and proposal stages, years from launch at the earliest, but Janus and Epimetheus continue their exchange regardless. In 2022, they swapped again. The 7 to 6 resonance shifted. Somewhere on the outer edge of the A-ring, the 7-lobed pattern either appeared or vanished, depending on which direction Janus moved. No camera was watching, no instrument was recording. But gravity does not pause for witnesses. It simply proceeds. And the fact that it proceeds, that this system continues to function exactly as predicted, even when no one is watching, raises a question that goes beyond orbital mechanics and beyond Saturn. What does it mean for two moons to behave this way? What does it tell us about the nature of order in the solar system? And what does the existence of Janus and Epimetheus reveal about how gravity shapes the universe when no one is designing the outcome? That is where we go next. We have now followed the story from its strange beginning to its intricate middle. We have seen how two small moons share an orbit that should be impossible. We have understood the mechanism that prevents their collision, the exchange of angular momentum that lifts one moon outward while dropping the other inward, reversing the approach and resetting the cycle every 4 Earth years. We have watched the consequences of that exchange ripple outward through Saturn's rings, sculpting edges, driving waves, leaving records in the structure of the ice that a spacecraft billions of kilometers from Earth could read like a text. Now it is time to step back from the details, from the numbers and the orbital radii and the resonance locations and the Cassini datasets, and ask what all of this means. Not what it means mechanically. We understand the mechanics, the physics is clear, the mathematics has been solved and confirmed. What we need to understand now is what the existence of Janus and Epimetheus tells us about the nature of the system they inhabit, about the kind of order that gravity can create, and about what it means for two objects to move through space as if they were following a script that no one wrote. Begin with the simplest observation. In the entire solar system, across all the planets and all the moons and all the rings and all the small bodies that have ever been catalogued and tracked, Janus and Epimetheus are the only known pair of comparable mass locked in a mutual horseshoe orbit. There's nothing else like them. Anywhere. This is not for lack of looking. Astronomers have surveyed the satellite systems of every major planet. They have tracked thousands of asteroids in co-orbital relationships with Jupiter, Mars, Neptune, and Earth. They have identified Trojan companions at Lagrange points throughout the solar system, small bodies riding patiently in the gravitational wake of larger ones, stable for millions or billions of years. Co-orbital motion, in the broad sense, is not rare, but the specific configuration that Janus and Epimetheus occupy, two bodies of similar size executing a mutual horseshoe exchange around a shared orbit, has been found nowhere else. There are asteroids near Earth that trace horseshoe-shaped paths in a reference frame rotating with our planet. A handful have been identified, tiny objects a few tens of meters across at most, following horseshoe orbits relative to Earth, with libration periods measured in centuries. They approach Earth from one direction, reverse their relative drift, and retreat the other way. The physics is the same as what governs Janus and Epimetheus. The same equations describe both systems, but the systems could not be more different in practice. Earth's horseshoe asteroids are specks. A typical one is perhaps 50 meters across, with a mass so small that writing it out in kilograms requires scientific notation, with a minus sign in the exponent. Earth, by contrast, has a mass of approximately 6 times 10 to the 24th kilograms. The ratio between Earth and one of these asteroids is so extreme, it is like comparing the mass of the Pacific Ocean to a single grain of sand floating on its surface. The gravitational interaction is entirely one-sided. Earth dominates. The asteroid responds. Earth does not move. Earth does not shift its orbit by any measurable amount. Earth does not feel the asteroid's presence any more than you feel the gravitational pull of a passing butterfly. The horseshoe pattern is imposed on the asteroid by Earth's gravity alone. It is a monologue, not a conversation. The asteroid listens. Earth speaks. And Earth doesn't even know it is speaking. Janus and Epimetheus are a conversation. Their mass ratio of 3.6 to 1 means both partners participate. When Janus tugs Epimetheus, Epimetheus tugs back, and Janus moves. When Epimetheus gains angular momentum, Janus loses it. When one moon rises to a higher orbit, the other drops to a lower one. The exchange is mutual. The interaction is reciprocal. And the resulting pattern, the interlocking horseshoe orbits, the Fourier swap cycle, the asymmetric but precisely balanced shifts of 20 and 80 kilometers, is a product of both moons acting on each other, not one acting on the other alone. This mutuality is what makes a system singular. In every other known co-orbital arrangement, one body overwhelms the other. Jupiter overwhelms its Trojans. Saturn's Tethys overwhelms Telesto and Calypso. Earth overwhelms its horseshoe asteroids. The dynamics are dictated by the dominant partner, and the smaller body simply follows. In the Janus Epimetheus system, neither body dictates. Both contribute. Both respond. The pattern that emerges is a joint production, a collaborative structure created by the gravitational interaction of two objects that are close enough in mass to matter to each other. And this system is stable. That word, stable, deserves more attention than it usually receives, because stability in orbital mechanics is not the same as stability in everyday life. A book sitting on a table is stable. It will stay there until something moves it. That is static stability. The Janus Epimetheus system is not static. It is dynamically stable. The moons are always moving. They are always changing their relative positions. They are always approaching, exchanging, retreating, approaching again. Nothing stays fixed. Everything changes continuously. And yet the overall pattern persists. Dynamic stability means that the system tolerates disturbance. If something nudges one moon slightly off its expected path, a gravitational perturbation from Mimas, a subtle tidal interaction with Saturn's rings, an ancient impact that deposited a fraction of extra momentum, the system does not collapse. The next exchange absorbs the deviation and corrects it. The horseshoe pattern reasserts itself. The swaps continue. The system is resilient in the way that a river is resilient. You can drop a stone into the current and the water parts around it, swirls briefly, and then returns to its previous flow. The stone changed the river locally and momentarily, but the river did not stop being a river. The Janus Epimetheus system has been behaving this way for a very long time. Theoretical models and the extensive cratering on both moons suggest the system has persisted for at least millions of years, and likely much longer. Some models tied to ring formation theories suggest the co-orbital configuration may date back hundreds of millions of years. To put that in perspective, hundreds of millions of years ago, the most complex life on Earth was still confined to the oceans. Dinosaurs had not yet appeared. The continents were arranged in configurations that would be unrecognizable on a modern map. And through all of that time, while entire lineages of life arose and went extinct on Earth, while continents collided and split and collided again, while the climate swung between ice ages and greenhouse epochs, these two small moons of Saturn were swapping orbits every 4 years, without interruption, without degradation, without anybody noticing until 1966. Across that span of time, Saturn's system has experienced perturbations of every kind: gravitational interactions with other moons, resonance crossings as moons migrated slowly outward through tidal interactions with Saturn, impacts from stray cometary debris, changes in the ring structure as ring material was lost to Saturn's atmosphere, or gained from the breakup of small bodies. Through all of it, the horseshoe orbit endured. The swaps continued. The moons kept trading places, absorbing each disturbance into the rhythmic exchange without ever losing the pattern. There is something deeply revealing about this. It tells us that the horseshoe co-orbital configuration is not a fragile accident. It is not a fleeting arrangement that happened to arise and happened not to be disrupted yet. It is a robust dynamical state, a basin of stability in the space of possible orbital configurations. The moons settled into this basin at some point in the early history of Saturn's system, and the physics of their mutual interaction has kept them there ever since. Gravity does not merely permit this arrangement, gravity actively maintains it. Every exchange reinforces the pattern. Every approach that looks like it should end in collision becomes, instead, the mechanism that sustains the system for another 4 years. This is where the story becomes something more than orbital mechanics. Because the system that Janus and Epimetheus create, the 4-year swap, the interlocking horseshoe orbits, the ring sculpting resonances that toggle on and off in perfect synchrony with the orbital exchange, has a quality that is very difficult to describe in purely mechanical terms. It looks choreographed. It looks planned. It looks as though someone or something designed the system to work this way. The moons approach on a schedule. They exchange positions with mathematical precision. The rings respond on cue. Everything interlocks. Everything meshes. There are no wasted motions. There are no extraneous forces. The system operates with an economy and elegance that you would normally associate with engineering. But no one engineered it. There is no designer. There is no plan. There is no blueprint. There is only gravity. Gravity is the simplest force in the universe in terms of its mathematical description. Two objects with mass attract each other. The strength of the attraction depends on their masses and the distance between them. That is the complete rule. It can be written in a single equation. Newton published it in 1687. Every gravitational interaction that has ever been observed, from falling apples to orbiting galaxies, follows this one rule, and from that single rule, applied to 3 objects, Saturn and 2 small moons, the entire Janus Epimetheus system emerges. The horseshoe orbits, the 4-year exchange cycle, the asymmetric shifts proportional to the mass ratio, the self-correcting stability, the density waves in the rings, the 7-lobed pattern on the A-ring edge that appears and disappears on schedule. All of it flows from one equation applied to 3 bodies interacting under their mutual gravitational pull. Nobody told the moons to swap. Nobody programmed the exchange. Nobody set the timing. The timing arises from the masses and the orbital separation. The exchange arises from the geometry of the gravitational interaction at close approach. The stability arises from the conservation laws that govern angular momentum and energy. Everything that the system does, every pattern it creates, every rhythm it follows, is a consequence of that one simple law of attraction, playing out across 3 bodies and the expanse of time. This is what physicists call emergence, a complex, structured, seemingly purposeful behavior arising from simple rules applied to a system with the right initial conditions. The rules are simple. The outcome is not. The law of gravity contains nothing about horseshoe orbits, or 4-year cycles, or 7-lobed ring patterns. Those words do not appear in the equation. Those concepts are not encoded in the formula. But when you apply the equation to Saturn, Janus, and Epimetheus, and you let the mathematics run forward through time, all of those things appear. They were not put in. They came out. The complexity was latent in the simplicity, waiting to be expressed by the right arrangement of mass and distance and time. You see emergence everywhere in nature once you learn to recognize it. A flock of starlings wheeling through the sky in coordinated spirals that look choreographed, but arise from each bird following 3 simple rules about speed, spacing, and alignment with its neighbors. A snowflake growing into an intricate 6-fold pattern from the basic geometry of water molecules, bonding at fixed angles in a crystal lattice. A river delta branching into a fractal network of channels, not because anyone designed the drainage pattern, but because water flowing downhill splits at obstacles and follows the path of least resistance. And each split creates new obstacles that cause further splits. And the cascading logic of that process generates a pattern of breathtaking complexity from an elementary principle. In each case, the individual rules are so basic that they can be stated in a single sentence. The resulting pattern is far more complex, far more structured, far more seemingly intentional than anything the rules seem to contain. The complexity is not in the law. It's in the consequences of the law applied across space and time. The Janus Epimetheus system is emergent on an astronomical scale. The rule is gravity. The initial conditions are two icy bodies on nearly the same orbit around a gas giant, and the result is a gravitational mechanism of startling precision. A pair of moons that swap orbits every 4 years without colliding, that sculpt the edges of planetary rings through resonances that toggle on and off with the swap cycle, that have maintained this pattern for geological ages without external correction or intervention. From one equation and 3 bodies, gravity built a machine, not a machine with gears and springs and a case, not a machine that anyone built or anyone maintains, but a machine in the functional sense, a system in which each part's behavior depends on and influences every other part's behavior, and in which the whole operates with a regularity and predictability that transcends the apparent randomness of its components. The inner moon speeds up, the outer moon slows down, they approach, they exchange, they separate. The inner moon becomes the outer moon. The outer moon becomes the inner moon. 4 years pass. They approach again. The same exchange, the same result, over and over, endlessly. The rhythm does not drift. The timing does not wander. The pattern does not degrade. Each cycle is as clean as the one before it and the one after it. Not because someone corrects the errors, but because the physics does not produce errors to correct. The exchange is exact because the conservation laws that govern it are exact. Angular momentum is conserved to the last decimal place. Energy is conserved to the last decimal place. And the pattern that results from that perfect accounting is itself perfect, repeating with a fidelity that no human-engineered machine could match over comparable timescales. This is what the solar system can do. Not through intelligence, not through design, not through any quality that requires a mind behind it. Through gravity alone, applied to mass, constrained by conservation laws, given time. The solar system builds structures that look like they were intended. Rings with sharp edges maintained by resonances with moons. Gaps cleared by tiny shepherds no larger than mountains. Waves driven by rhythmic gravitational tugs that have been repeating since before the Earth had oxygen in its atmosphere. And 2 moons that swap orbits in a cycle so precise it reshapes the ring edge every time it happens, leaving a record in the ice that a visiting spacecraft can decode 4 billion kilometers from the planet where the engineers who built that spacecraft were born. We tend to think of order as something that must be imposed. A room becomes messy unless someone tidies it. A garden grows wild unless someone tends it. Entropy increases. Disorder is the natural state. And in a general sense, that is true. The universe is heading toward maximum disorder, toward heat death, toward the long equilibrium of maximum entropy. But along the way, in pockets, in specific configurations, in systems where the right initial conditions meet the right physical laws, gravity creates order, real order, measurable, repeating, self-sustaining order. Not permanent order, not eternal order, but order that persists for hundreds of millions of years, which is long enough to matter, long enough to astonish, long enough to make you wonder how something so precise could arise from something so simple. And now consider the emotional weight of this image. 2 small moons, irregular, cratered, ancient, made of water, ice and dust, porous enough to float on water if water existed on that scale, scarred by billions of years of impacts, each one rotating slowly with the same face forever turned toward Saturn's banded clouds, each one smaller than many cities on Earth. Janus is about 178 kilometers across. You could drive that distance in under 2 hours on an ordinary highway. Epimetheus is about 117 kilometers across. A determined hiker could walk it in a single long day. These are not grand, imposing objects. They are modest, unassuming. If you were touring the Saturn system and someone pointed them out, you might nod politely and turn your attention to something more spectacular. Titan's orange atmosphere, Enceladus's geysers of water vapor shooting hundreds of kilometers into space. The rings themselves, that vast luminous disk that makes Saturn the most visually stunning object in the solar system. But these 2 small moons are doing something that nothing else in the solar system does. They are sharing an orbit that by all appearances should not permit 2 occupants. They're exchanging positions every 4 years with clockwork regularity. They're performing a gravitational maneuver that has no parallel among any known moons or planets. A maneuver so precise that it reshapes the structure of a planetary ring system every time it occurs. And they have been doing it for longer than complex life has existed on Earth. They do not know they are doing it. They have no awareness. They have no intention. They are ice and rock and vacuum and gravity, nothing more. And yet the pattern they produce has a beauty and a precision that stirs something in the mind of anyone who understands it. There is a satisfaction in watching something work perfectly. A deep, quiet satisfaction in seeing a mechanism operate without flaw, cycle after cycle, with no input and no maintenance, and no possibility of failure as long as the laws of physics hold. Janus and Epimetheus offer that satisfaction at an astronomical scale. They are a proof that the universe is capable of creating order, real, measurable, repeating, predictable order from nothing more than mass in motion. The moons do not survive because they are lucky. That needs to be said clearly. Because the first reaction most people have when they hear about co-orbital moons that swap orbits without colliding is that it must be a lucky coincidence. It sounds like a close call repeated forever. 2 objects, just barely avoiding catastrophe each time, sustained by some improbable thread of fortune that could snap at any moment. But that is not what is happening. Not even slightly. The avoidance of collision is not luck. It is physics. It is built into the geometry of the interaction, woven into the mathematics as tightly as the Pythagorean theorem is woven into right triangles. Given the masses, given the orbital separation, given the direction of the gravitational pull at the moment of closest approach, the exchange is the inevitable outcome. Collision is not narrowly avoided. Collision is not even a possibility within this configuration. The same force that brings the moons together is the same force that swaps their orbits and pushes them apart. There is no moment of danger. There is no near miss. There is no hair's breadth escape. There is only the exchange, as certain and as reliable as the sunrise on a planet with a stable axial tilt. The system does not dodge destruction. The system was never in danger. The physics forbids the collision as surely as it mandates the swap. And that certainty, that reliability, is what makes the system beautiful rather than merely interesting. Interesting things happen once and are noted. Beautiful things happen again and again, revealing in their repetition a structure that transcends any individual occurrence. A single sunset is pretty. 1,000 sunsets, each one governed by the same geometry of atmosphere and light, are beautiful because the pattern endures. The Janus Epimetheus swap is beautiful because it repeats. Because every 4 years, the same gravitational logic produces the same result. Because the pattern has persisted through millions of cycles without degradation or drift. Because it will continue for millions more, or tens of millions, or hundreds of millions, as long as Saturn holds its court of moons and rings, and the ancient ice of Janus and Epimetheus endures against the slow attrition of micrometeorite bombardment and the patient pull of tidal forces. Tonight, we have followed the story of 2 moons from their confused discovery in 1966, when astronomers spent 12 years trying to force 2 separate objects into the straitjacket of a single orbit. We followed them through Voyager 1's confirmation in 1980, when cameras on a passing spacecraft finally showed 2 distinct bodies where everyone had assumed there was one. We traced the mathematical understanding of their horseshoe orbits, the work of Dermot and Murray and Yoder and others who demonstrated that the configuration was not a fluke, but a stable, dynamical state. We walked through the counterintuitive orbital mechanics that makes the swap work. The paradox that gaining energy means slowing down and losing energy means speeding up. We watched through Cassini's tireless instruments as the spacecraft recorded the exchange and its effects on Saturn's rings over 13 years of close observation. And now we arrive at this moment. This question: what does it mean? It means that the solar system is stranger and more beautiful than a casual glance reveals. It means that gravity, the simplest and most familiar of the fundamental forces, the one we experience every moment of every day without thinking about it, can produce behavior that looks like magic until you understand it, and looks like engineering once you do. It means that 2 moons can share an orbit that appears impossible, can approach each other on a schedule that appears catastrophic, and can exchange positions with a precision that appears designed, all without any intelligence, any plan, or any force beyond the mutual gravitational attraction of mass for mass. It means that the universe does not need a designer to create order. It only needs laws. Consistent, simple, universal laws applied to matter distributed across space and given time. From those ingredients, gravity builds horseshoe orbits and ring edges and density waves. From those ingredients, gravity turns 2 chunks of ancient ice into a mechanism that has been operating without interruption since before the first fish crawled onto dry land on a planet 1 billion kilometers away. It means that choreography without a choreographer is real. Mechanism without a mechanic is real. A dance without a dancing master is real. And the dance does not end. Right now, as you listen to this, Janus and Epimetheus are circling Saturn. One is on the inner track, moving slightly faster. The other is on the outer track, moving slightly slower. The gap between them is closing, a fraction of a degree each day. In a year or 2 or 3, they will approach within 15,000 kilometers off each other. The gravitational exchange will begin. Over about 100 days, angular momentum will flow from one moon to the other. The inner moon will climb outward. The outer moon will drop inward. They will trade positions without touching, without approaching closer than the diameter of a planet, without any drama visible to the naked eye. The rings will respond. The resonance locations will shift. The seven-lobed pattern on the outer edge of the A-ring will either appear or vanish, depending on which direction Janus moves. And then, the quiet coast will begin again. 4 more years of silent convergence. 4 more years of the inner moon gaining ground on the outer moon, until they meet again, and swap again, and separate again. No one will be watching. No spacecraft orbits Saturn today. No camera records the moment. No human eye will see the moons approach each other against the backdrop of Saturn's cloud bands. No instrument will measure the instant when angular momentum begins to flow from one body to the other. But the physics does not need an audience. Gravity does not perform for observers. It does not wait for attention. It simply acts, continuously, silently, in the dark. And 2 small cratered icy moons, each one modest enough to fit inside a small country on a planet they have never visited, continue their ancient exchange in the space beyond the rings, circling Saturn every 17 hours, gaining ground or losing it, approaching or retreating, always. Somewhere out there, right now, one of them is a fraction of a degree closer to the other than it was yesterday. Tomorrow it will be closer still. The gap is closing. The exchange is coming. And when it arrives, it will happen the same way it has happened every time for millions of years. Silently, precisely, inevitably. 2 moons will trade places. Neither will touch the other. And then it will begin again. They are Janus and Epimetheus, 2 moons of Saturn, the moons that swap orbits without colliding, and they are still dancing.